And now I'm very happy to announce you Carsten Nohl. Carsten Nohl is a researcher who has also researched, sorry for that. Carsten Nohl is the guy who also researched the malware chip, who did also the package.
And who hacked DECT phones.
Yes. Yes, who also did the DECT hacking, and now he has hacked some smart cards. And please give Carsten a warm applause.
Thank you very much. This is an enablement talk as opposed to an exploitation talk. We're not releasing any how to hack your smart card results today, but instead show you a way of do that yourself. Quick round of questions before we start. How many of you have ever analyzed a piece of software? Looked at its behavior, looked at it in a disassembler. How about a smart card? Okay, couple people, maybe dozens. So you do understand, though, that there is software running on smart cards that could be analyzed just the same way you analyze any other piece of software. In fact, it's pretty simple software since it runs on scarce resources. It's very old assembler code, usually not too obfuscated. So all of you who did analyze software before, probably you do want to look at some SmartGuard software as well, but you don't yet have a way of extracting the software from these little cards. And that's what we want to change today. All right, let me start by just explaining what I mean by smart cards, since that term can be somewhat misunderstood, and the wide usage of smart card chips is probably underappreciated. I'll then explain what the security evolution of smart card has been and where industry puts its efforts to making these cards, these chips more secure. I'll then show how they kind of missed one attack vector, show how we exploited that, and touch a little bit on how future chips could be made more secure, if that's even in anybody's interest here. All right, smart cards are not actual cards. The term refers to little chips that, among other things, are found in plastic cards, like in pay TV. So those cards you put in a pay TV box, that's where the name smart card comes from. And in fact, that was the first industry that tried to solve a problem that today appears to be omnipresent. So in pay TV, people wanted to hide secret keys from the people they gave the keys to. So if they handed you as a pay TV customer a card with a key on it, they wanted to prevent you from extracting that key and making multiple copies of the same card. So everybody who got a key paid the subscription. Now that very problem today is found pretty much in every device. Newer smartphones have a secure element inside that protects NFC encryption keys that in the future should encode maybe your ID card, but certainly your credit card, will provide authentication badges, will provide all of this inside your smartphone. Now, all of those applications are just named. They also use smart cards today. So pretty much any card that does some form of encryption, either wireless or with a little golden or silver pad of pins, is a smart card today. It's a billions of units per year market where surprisingly few manufacturers actually play a role. So there's probably only 5 relevant companies that supply chips for all of these solutions, be it the TPM in your ThinkPad or the chip in your contactless Visa or MasterCard. So breaking any one of them or being able to analyze any one of them opens a whole range of applications. So take this as a bit of encouragement to, if you're a frustrated software analysis who's sick of looking at hundreds of versions of some Windows library and see your target move all the time. Take some analysis time instead to look at smart cards. Much higher impact, much higher leverage. So that's the analysis target. Let's though look at one of these cards so you get a better idea of what actually happens inside of these chips and how this is very similar to systems you have been using in the past. Pretty much a smart card chip is a fully integrated computer with, underneath this metal plate, or zoomed in here, a CPU. This is an 8051 CPU, so it speaks the same instruction set as one of the first Intel processors. It runs on, I think, 15 megahertz, this card, 8-bit architecture. So in terms of computing power, it's incredibly slow. But it does have to do a few things fast, in particular cryptography. Usually these cards are used to execute some cryptographic protocols. So it does have crypto accelerators. I believe this is an AES engine. So it does AES in just a few clock cycles, while everything else is really slow in this 8-bit architecture. The chip area is dominated, though, by memories. Up here, there's flash or EEPROM, so this is read-write memory. Down here are 2 banks of ROM, so that's once writable, basically through manufacturing. The program code, the operating system, some application code is written to these, and it's not changeable throughout the lifetime of this card, so no possibility for patch management should anybody find software bugs in here. And then I believe underneath here is RAM. So it's a fully integrated computing system with all the components you'd usually find on a motherboard. There's some additional routing and all this here. So what's the type of attacks people have been launching against smart card chips in the past? There's two kind of independent lines of attacks. One has shown up earlier throughout the evolution of these cards with the first pay TV cards, and the other one showed up a little later and is more prevalent today. So the early attacks worked by reading out memories such as these optically. I'll show you on the next slide why that is possible and what the effect of this is. But let me, while on this slide, explain the second attack. The second attack works by probing little wires. You see all these wires connecting in between here and all these routing wires. Some of these wires will carry sensitive information while the chip executes. Could be the AS key while it's loaded in here. Could be some secret assembly code of a non-public protocol. Could be anything that this chip sees. So there are 8 wires, because 8-bit architecture, that carry everything that's ever moved from one part of this chip to another, read out from the memories, for instance. And of course, being able to read data from these wires gives you all the secrets of this card. So that's what people like Kristanovsky, and I should say that this is work done with Kristanovsky as well as Starbuck. So thanks to both of those for helping generate these results. So people like Kristanovsky with highly sophisticated machines and years of experience do open these chips and then put tiny needles on exactly the right 8 wires and read everything out. And that's the attack model that industry has in mind when improving these chips. In particular, they're trying to improve these chips by piling up layers and layers of basically useless stuff on top of the chip, on top of these 8 wires, so you can't, with your tiny needles, get through to the wires anymore. Chris showed on this chip, actually, a year and a half ago at a Black Hat conference, how we did find the right 8 wires nonetheless and kind of scratched away everything that was on top and rewired it to still be functional, and how we could read this out. A tech that I would put effort wires at somewhere between $80,000 and $100,000, right? So if this is a state secret, certainly people will spend that kind of money, but not anyone here to do some hobby analysis. So let's go back to the other attack, the reading out memories optically. The one attack that happened much earlier was the first pay TV cards. These are some images of ROM bits, so the big areas down here. If you zoom in enough, it will probably look like this stuff on the left. The right is from another type of chip. And you do see the actual bits in here, right? You see zeros and ones. And in fact, you see in this memory, the one on the right side, how this is the end of ROM, so how it ends in FFFFF. They just didn't fill up the ROM, so there's a static pattern in here. And these images can be generated just with an optical microscope in a lot of cases. Depends on the feature size, but even if they need some more specialized equipment, getting images like this, couple $100 as a professional service. Now, how did industry respond to the threat of people just reading out the whole operating system, all the applications for the analysis? That's what we want to do, right? We want the application code to then look at it in a disassembler. They started encrypting the contents of this memory. And if I can go back to the other slide just once more. In addition to the CPU that I've zoomed into here, there's an additional encryption decryption function just here. It's size-wise maybe half as big as the AES function, right? You see here and compared to this. And this function is a completely secret, not documented encryption function that the chip uses internally to encrypt all of its memories. So instead of this pattern, of FFFFF that you can optically even see here, this same memory would have a more random pattern, one that doesn't give out the code anymore when put into this newer smart card, right? And that has, for the past 10 years or so, prevented this line of optical readout attacks. Now, we're going to bring it back now. We have the goal of reverse engineering this memory encryption function so that if you do read out the memory just optically and you understand how the encryption works, so you can translate what you read out into something you want to analyze, and all of this without the little needles and without the whole effort of having to operate basically on a running chip. So this is kind of static versus dynamic analysis. Before explaining actually how we did reverse engineer it, a few words on coverage. So does this work on just the one chip we looked at, or is this a general attack across all these 5 vendors and maybe two cards each? So there's 10 smart cards in the world. We looked at one. This same method will work against every single one of them. The reverse engineering, the memory encryption, and then reading out memories optically. What does change, though, is where the encryption function is located. So with the card we just looked at, it was nicely separated, and it was clear what exactly we'd have to reverse. In other cards, it's not that clear anymore. Here's a more modern card. Here, too, we clearly see the memories, right? Again, this would probably be a big area of, I don't know, it could go either way. So there's ROM and flash here. And there, of course, is a memory encryption function, but this memory encryption function and the CPU core and the AES function is also an RSA accelerator, and all of this is piled up in this big blob of random logic in the middle. So reverse engineering this, of course, is still possible, but maybe require some more smarts in defining your analysis target. Instead of just reverse engineering everything in one particular area, you would, in this case, start at the output of the ROM, see where those lines go, reverse engineer everything there, see where those lines go, and so forth. But I'm getting ahead of the story. We still haven't seen how we did reverse engineer it for the one card. One last word on protection mechanisms, and this is just to say that this doesn't impact our analysis at all. Smart cards do protect themselves today with these meshes to prevent Chris's needles from getting to the chip. We just take off the mesh and do our analysis anyway. So the whole last 10 years of evolution in chips, better meshes, more meshes, 2 meshes, does not impact this type of analysis at all. So in some way, the evolution of chips has completely disregarded the possibility of reverse engineering. And the encryption function found on the chip today, this particular chip, even though it has gone through many design cycles, is still the exact same function that it put in 10 years ago as a novel idea. Right? So, what does it take to reverse engineer a chip? Basically, the challenge put in software terms, we need a disassembler. We need a way of bringing back a compiled instance, a kind of non-human readable instance of an algorithm into some human readable form, right? Basically, IDA Pro for chips would be nice. Where you just give it whatever the manufacturer gives you, in software case a binary, and bring it back into an analyzable form. And Martin Schobert in Berlin has been working on solving this challenge ever since our MIFARE work, actually. So for the past 4 years, he's just finished his diploma thesis on this topic, actually. And he created the first silicon reverse engineer tool that's open source. Supposedly, there are similar tools available for lots of money, mostly from China, where this is kind of a pirating tool too. If you reverse engineer somebody else's chip, you can then clone it. But none of the software, I don't think, is used in security analysis yet. So here now is an open source tool for all of you to use, and hopefully also used for security work. The process in which this tool is used, of course, consists of some additional steps besides just the reverse engineering, since you don't start with a nice binary file in a computer. In fact, there's nothing in the computer when you do start. You first have to get your data into the computer. So the steps, though, haven't really changed from the MIFARE project. It still consists of taking several instances of the chip and filing them down, polishing them down to different layers of this 3D structure, taking pictures of each of the layers, piecing those together in the computer to basically have the binary file, and then running the DGAT program on it. The DGAT program will convert the images through a semi-automated process into a human-readable algorithm description again. Right? The programming language used to describe chips is either Verilog or VHDL. DGAT supports both. So over the last couple of years, DGAT has become more scalable in mostly 2 dimensions. The first dimension is what I just explained, that the results of DGAT are very expressive today. It won't be just a description of this is connected there and this is connected there. It generates actual compilable code that you could, in theory, use to, again, synthesize the chip and then have a second hardware copy of what you had before. Because losing losing a lot of elegance of the initial design optimization. So you'd have something that's functionally equivalent, but probably 100 times larger before somebody, again, starts optimizing that. But you also now have a description that somebody, just like the IDA Pro users among you, can start annotating, sorting through, finding functional blocks, and start understanding the algorithms implemented. And in particular, in our case, this one encryption algorithm. Right? So this is the DGAT software, and Let me actually run that so you've seen in action that even somebody like me can use this. So this is some chip. In fact, that smart card chip we want to extract the encryption function from, open and dgate. So it has several layers of images. Starting at the lowest layer with functional blocks. So these would be your lines of assembly code, right? There's an XOR here, for instance, right? Yeah, we obfuscated this a little bit because we're not giving out the function quite yet, responsible disclosure and all of that. There's an AND gate. So some are just too simple. There's no obfuscation needed. There are 4 transistors. You see 1, 2, and another 1, 2, and they're connected in such a way that this forms a 2 NAND function, right? And then this 2 NAND function on the layer on top is, well, this is connected to somewhere outside of the area of this chip, but its inputs, A and B being, A and B, weird, where's the Y? Well, let's look at this down here, it's more clear. So the A and B, the B is connected to this other gate here, so the XOR's output forms an input to this 2 NAND, and then the A gate seems to be connected yet another layer on top. Probably this connection, so it goes to this other 2 NAND gate here. And that's exactly the type of information we want to capture now in a more manageable form. So somebody using this tool would, well, first of all, annotate the gates, as we've already done here, and that's the process of when you just start without any annotation. So this is the pictures as you would actually take them with a microscope. You would start finding functional blocks, and that's not hard at all. So for instance here, you see this gate is exactly the same as this gate. So it seems clear that this is a functional unit. And in fact, the same gate again is here and here. The gate and this gate again occurs here, just mirrored. You see this arc? The same as this arc, right? It's the same gate reappearing, taken from a library. You may, if you look at such pictures for the first time, have a hard time kind of distinguishing everything, especially when it gets more noisy, like in this area. However, let me assure you that this is the most heavily obfuscated chip we've ever seen. So it doesn't get any worse than this. With almost all, especially more modern chips, the gates are neatly separated in rows, and it's very clear where every gate starts and ends. So in any event, so you would start by marking one of these gates, and you'd tell the gate, okay, I think this is a gate, try to find other instances of the same gate, and it will do pattern matching, and will say, boom, here's one, boom, there's one, there's one, there's one, there's one. And so you get some coverage, and then you start searching for the next one. Again, let it search, and not much later, you have full coverage of your chip. You need to, for each gate, look at them one by one, finding out the actual function. And again, this is highly obfuscated, so, and even these are not so hard to figure out. All the other chips we looked at, they're actually trivial to figure out. If you want some examples, if this seems like magic to you, go to siliconzoo.org. There's lots of examples of how little functional units and described with what they actually do. So that's the first step. That gives us then basically this map of all the assembly instructions in your binary. What doesn't exist yet is a flow. So you just have them all kind of unsorted on your table. And what's missing is the order in which the assembly instructions are executed one by one. And that are these wires that connect them, where the output of this goes to the input of this. So that gives it some order, right? Where different instructions are executed on the same data, one by one. And that's easily taught to dgate by telling it, okay, so starting on the highest layer, I see there's a connection going down, there's one going down, there's one going down, there, and so forth. And then there's wires, for instance, going from here to here, and then one wire from here to here, and a long wire from here to here, and then further down. So you can see how somebody spends a couple of hours annotating all these wires. There is a function to do this automatically. It doesn't work on this type of image though, since the colors are not really different enough, so it can't really distinguish the wire cutting underneath here from the wires going on top. But with nice pictures like this one, taken with a scanning electron microscope, with much nicer edges, separation between wires and the rest, the tool actually automatically finds all these wires. But in either event, there's just a couple of hours of work involved. There may be, including some debug runs, a few days. However, work that, of course, can be highly scalably outsourced to some cheap labor. So I'm imagining an Amazon Mechanical Turk plugin where people just click on wires all day long, maybe for 1 cent per 10 wires. And they do silly tasks like that already, like annotating street maps, for instance. Very similar task. Where do streets go on satellite pictures? And that really are all the steps required for the tool now to say, to understand where the circuit is. So when there's a wire running underneath, like in here, and then a via connecting two wires and a wire cutting above, then it understands that all these pieces are fitting together with some variance, of course, and that there actually is a grid being formed. The tool can also notify you of potential errors. So what never happens in silicon, for instance, is that two outputs are connected to each other. Of course, they would be fighting, or that there are inputs of gates being not connected to anything. So there's some rules to what the circuit has to look like, and the tool will notify you of all the rule violations. So it does the first debug run, basically, for you. So eventually, you reach a Verilog or VHDL representation of the whatever is represented in the pictures you took. Are there any questions so far? Because now I kind of want to switch gears and talk about the crypto that we did find. Any questions? Can you walk up to the microphone? Thank you.
Just what kind of process is being used here? I mean, how many metal layers and what kind of process is this?
So that differs basically by every picture I've shown. This picture is from, well, where's that? I think this is the crypto inside the DEC chip. It also had a smart card core, but then they put the DEC crypto as an extra functional unit on the same chip, and this was something like 600 nanometers. So super old, but still in use today. These chips just get designed once and then used for 10 years until the standards change, right? This smart card here, also optical picture, so it's probably something 200 nanometer, right? 180 nanometer is the edge, the last possible size that you can picture optically. Everything underneath, the wavelengths of light is too big, so optical microscopes don't see the gates anymore. However, even in a 180 nanometer chip, the upper layers, of course, are much bigger structures. But everything 180 and below, you will need to use a scanning electron microscope or a FIB, at least for a few layers. And this chip, for instance, interestingly enough, the one where this is the memory encryption function that we're reverse engineering, have been reverse engineering and presenting today, that comes in all kinds of different feature sizes. So this exact function, this one footprint of a memory encryption function has been found in smart cards for 10 years. So you find this in all the way from 600 nanometers down to like 210 nanometers, right? And you basically get to choose your target for reverse engineering. Just take the one with the easiest imaging method, and the results apply everywhere. Yeah. On that thought, they also manufacture this chip with no mesh. So again, you get to choose whether you want to attack a chip with a mesh or without a mesh, right? So I don't know why that is, why they give you an easier target for analysis and make the results applicable to higher value targets also. So there was another question and then it disappeared again? Yeah, go ahead.
How many pictures would you have to take for a typical attack?
How many pictures? That's a good question. So this unit we're looking at here is maybe, of course depends on your camera, but something like 50 pictures per layer. And there's, also you asked about the number of layers. There's 2 meta layers that are relevant for the encryption function. There's more meta layers on top. But it's basically, they're functional units. They're kind of routed on the lower layers. And then those functional units are routed amongst each other on higher layers. So let's say 150 pictures. But there's automated picturing equipment, of course, that takes a picture, then moves the chip a little bit, takes a picture, moves the chip, right? So it's really just 3 runs of pictures, 1 for each layer. Follow-up question?
Yeah, sorry. The meshes are then standard metal layers? The top metal layers are meshes, or is there something else above the topmost metal layer?
Most chips now have as a top metal a mesh. So what we saw in here. So this chip is functionally complete, right? And this has, I think, 4 metal layers up to this point, and then I put a 5th metal on top. That's just a little snake going all the way across over and over again, and the chip tests whether the snake still exists, so it takes a measurement from one end to the other, and when it's not intact anymore, the chip won't boot. Right? So it will never put any secret information on its little wires. So if you try to get with your needle underneath this mesh, this prevents the chip from exposing sensitive information. And today these meshes are a little smarter. They're like interleaved snakes and pseudo-random patterns among them. But there's always a way of course, finding the 2 points that should be connected and connecting them in another way, not through this mesh, and then drilling your hole in the middle after all. But that's what Kristanovsky specializes in. Yeah. One last question.
As soon as you found and identified the logical units on the pictures and draw the lines, can you get some VHDL output, like code?
Oh, that's a good question. And we're debating implementing that or not. We never have because we never needed it. But of course, you could kind of have the tool automatically find the transistors, then automatic or even manually find the transistors, have somebody connect the transistors to each other within these functional units, and then have a Verilog on, what was that level then? So we're reversing on RTL level and 1 layer below. But yeah, no, we don't do that. It's too much fun to look at these gates and figure out what did they want to implement here, especially when it's obfuscated. And in each of these projects, it's probably 1 or at most 2 days you spend on this. So we don't want to take the fun away from us, and coding this up would be a lot of work. Yeah. One last question after the last question. Yeah.
If you have some spare time after the talk, please explain how you recognize the functions.
Sure, yeah, let's talk about that after the talk then. All right, so that's the type of output to be expected by this tool. It does export Verilog and VHDL, but of course there's viewer programs for that. And so it's not quite assembly binary, mostly because it's highly parallel. So instead of having one instruction after the other, there's maybe 100 streams, 100 threads executing at the same time. And at the end of the clock cycle, they all computed something at different speeds. And this is kind of the data flowing through from left to the right. But each of these functional units performs some operation on the data and some mathematical function. So what do we find in this smart card? No surprise, of course, proprietary crypto, bad crypto. In this case, though, a crypto to which no good alternative exists yet. This is a crypto that, as I said, is basically undocumentedly doing its work while the rest of the chip executes. So it's kind of an on-wire encryption, and it has to execute a full cycle, a full block cipher in half a clock cycle, right? DES is implemented on this smart card, and that's probably the most hardware-optimized block cipher I can think of, at least of the standard ones, and that takes 16 clock cycles on this chip. So they try to create a block cipher here that's, you know, something like 30 times faster than DES, while providing some reasonable level of security. And of course, that latter part didn't work out so much. It's a 64-bit block cipher that mostly consists of key storage. I'll show you on the next slide why that is. That then takes these 64-bits of key, mixes them, runs them through a ROM lookup table, and the output of which is then kind of first blown up and then again demultiplexed into the 8 bits you need to decipher the data bus. This works in both directions. So it's basically a block cipher in CBC mode with the address that you're currently accessing as the initialization vector. So the same data element encrypted at different positions in memory will have a different representation so that you don't see patterns. If again you put in FFFFF, it will look different, the Fs in every memory position, right? So as I was saying earlier, we're not quite yet releasing this. If you do want to get started and you have one of these smart cards and you really want to code out, get in touch. We'll help you with that. So we definitely don't want to hinder the analysis. We're actually trying to encourage. But also this is so widely used, has been for 10 years, the market leader in smart cards that there's a fair warning now for all these systems to upgrade to some other chips or make sure their software doesn't have any bugs, and please put it on the internet then if you're a vendor, right? But 3 things to do point out that I thought was kind of neat when analyzing this. First of all, this memory area, this lookup table, is different for every chip. Not for exactly every chip, but for every production run of chips. So different different customers and even different versions of chips for one customer will have a completely different encryption function. Same structure, but completely different mapping. I thought that was a neat idea. So kind of to prevent exactly what we are doing now, reverse engineer it once and then make this work on all the chips of this line. However, the way they do differ is by putting in another ROM and changing that ROM, and we already know how to optically read out ROMs, so this is just one more variable to fill in during the analysis. This is nothing that would make the readout of ROM any more complicated. So if this was a flash or something, great idea, but they kind of didn't think it through all the way to the end, changing this only in ROM. 2 other things to point out, and I'm now kind of talking about the upper and lower parts of this 3-part function. In fact, there's 16 little blocks put together in 4 bigger blocks. And so each of these bigger blocks holds 16 bits, hence each of the little blocks holds 4 bits of key. However, 3 different keys are stored in here. So the ROM is encrypted differently for each production run. The flash can, in theory, be encrypted differently for every individual card. And the RAM is encrypted differently every time you boot up the card. Because, of course, when you start, the RAM is empty, and everything you want to read from RAM, you first have to write into RAM. So you can choose a different encryption key every time. And the random number generator for that actually lives within the encryption function. So it generates 64 random bits every time. And then it took me a while to figure out what these transistors do. So this is the smallest random number generator I've ever seen. Just 4 transistors to generate 2 random bits. And it does work. We did measure this, with the probing needles. This does come out differently a lot of times, right? So very neat design here. However, note that they're building a really weak encryption function here, probably scarce in resources and all of this, and they store 364-bit keys. So a lot of the available resources are just spent on storing the keys. So the last thing to point out about this encryption function, as I've shown down here, and as I've actually mentioned before, so this chip goes way out of its way, and then only for the encryption function, no other part of this chip, to obfuscate the gates. So usually when you look at logic, it's pretty easy to figure out what it does. But with these gates, that's not the case at all. They are way too complicated for the simple function they perform. And in fact, these two gates perform exactly the same function, and they look nothing alike, right? So that's the level of obfuscation that I tried to put in. But you know, maybe that then extended analysis from 1 day silicon gate puzzling to 2 days. Not a giant leap, but at least they've tried. Yeah. So let me encourage you again to start analyzing this by, for the moment, getting in touch with us. We'll extract this code for you. Later on, hopefully, either us or, you know, now that the tool is at this level, you reverse engineer this function, maybe not just for this chip, but for other chips, and start sharing them and start opening up these fortresses. Because to just wrap up this part of the talk, smart cards were, especially around pay-TV, designed for one purpose: to keep a secret key secret. Today, they're being abused for a completely different purpose: to cover up software vulnerabilities, to keep software away from the people that would point out bugs in your software. So, in some sense, smart card chips are too secure, at least around software, keeping software secret. And the neat thing about the attack, as I outlined it, there really is no abuse potential for applications that use smart cards the correct way, as in store a secret RSA key and then execute a standard RSA type protocol. We don't extract anything from EEPROM here. We don't extract anything from flash here. Those are the memories that would be used to store keys. We do extract everything that's in ROM. That's usually some proprietary operating system, an embedded Java runtime environment, and some Java applications, right? None of which has ever been publicly analyzed, right? So you can imagine that, you know, short of any pressure to write good software, because the smart card does protect this stuff as much as it does protect the secret keys, the quality of at least some of these software pieces deteriorates. And we do find, for instance, Java bugs in SIM cards. So one potential exploit scenario you could imagine is over-the-air exploitation of SIM cards. There are over-the-air update protocols, so somebody could deploy a virus to your SIM card that sees all your text messages, can initiate calls, may read your GPS transmitter or whatever the interfaces are implemented, and deploy that to your phone over the air to a platform that allows for no patching whatsoever, right? Well, just some ideas for further research. All right, what would smart cards actually need to do to prevent this? So if there was some legitimate need to keep information in ROM secret, that would require action from two different groups, I believe. First of all, of course, from the people building smart cards, acknowledging this as a weakness and doing something about it. Nothing has been done against reverse engineering ever since they put this encryption function into the chips, and that's more than 10 years ago. So we now caught up, and it took a long time, but we now caught up, and they are now asked to kind of do the next step and keep the game fun. However, there's also of course, actions required from people using smart cards and designing systems around smart cards, and I'll get to that in a minute. But first, what can manufacturers do? Simple step, and one that's already been taken, not for security considerations, but mostly for cost pressure on these cards. Make them harder to analyze by scaling them down, like go below 180 nanometers, so people need much more expensive microscopes, but also put more stuff onto the chip. Like a GSM handset chipset, or even the DEC chip we looked at. It's huge compared to traditional smart card chips. So there's a lot more noise. All this silicon, what are you going to analyze there? So building more kind of system-on-chip type devices makes analysis much harder. And that, of course, is what's happening. Of the 3 hardened microcontroller / smart card chips in the phone, probably just one will survive and kind of suck up the other one's functions inside. So that's ongoing. But more directly in response to this research, the simple exploitation of these memory encryption functions should be prevented. And I didn't yet say, and I probably should have when explaining how of course now the memory encryption attack works, how we go about decrypting it. So we read out the memory. We have an encrypted instance of the memory from optical ROM images, and we do have the decryption function, reverse engineered with this dgate program to decode it. Now, one thing that's missing, of course, is the secret key to decrypt it. And where would that be stored on all these smart cards? It's in the ROM, right next to what you just read out. Right? So you get all 3 pieces to the puzzle, and you decrypt the software. Now, this third fact that the key is stored in the ROM is, of course, stupid. Why to store the key next to what you're encrypting? I mean, who would do that in any other application? But on smart cards, you don't have many places to store it. But there's one much more secure alternative, that is the flash or EEPROM memory. Right? So by just storing this one 64-bit value in flash, or make that 128-bit to be a little future-proof. So spend 128-bit of flash, and these devices have something like 72 kilobytes of flash. Would prevent any of the type of analysis we're doing for the moment, since you can't optically read out the flash. A 0 and a 1 in the flash differs by something like 5 electrons that are either stored in there or not. So that there's actually no equipment I can think of, not even an atomic force microscope that would allow you to distinguish a 0 from a 1 in the flash. So the only way to get the data out to flash is to run the chip and have the chip read out the memory and then somehow sit on the wires where that happens. However, let's assume they did that. What has to come in addition to the secrecy of this key is a strong encryption function. Because with this encryption function that executes in half a clock cipher, 64-bit block cipher, we don't need the key to decrypt it. There's simple cryptanalysis you can run, assuming some patterns in memory that reveals the key from just looking at the memory. So getting the encrypted version and knowing the encryption function is enough to decrypt it. This is how bad this encryption is. However, of course, replacing this with anything else is hard. There is no alternatives yet. So for the cryptographers in here, or math geeks, here's a new challenge. And I didn't know there were any challenges left in cryptography after we have ECC and RSA and AES, and there's all these standard ciphers. Here's a new challenge. Create a somewhat okay encryption function that executes in one clock cycle on a small silicon chip. Right? That's really what's needed to protect this. And of course, this is several years out until people actually find these functions. So I guess that's good news for anybody who wants to analyze the software in smart cards. This will be possible on every smart card existing today, and until this research challenge is solved and keeps people from hiding bugs in secured hardware. All right. I'll keep this short since I don't think there's many kind of smart card company customers, decision makers in here. So, but if there was one, here's the message: don't put too much value on these cards. It's ridiculous to play in the pay TV arena where breaking a single card will give criminals millions and millions in automated revenue through selling these fake cards. The pay TV is a particular industry, and they have this one-way communication trust model that doesn't exist anywhere else. So unless you're in pay TV, keep the value of each of these cards low. Do what the banks do. Allow people to take 500 euros out of their ATM machine every day and not more. So copying a bank card gets you 500 euro today, maybe 500 euro tomorrow, and then the card gets blocked, right? Then you again go to Chris and have his needle do the magic and probably spend another 50,000 on equipment, and again you extract 1,000. So at some point, no criminal business case exists anymore. And a real-world example from France, research that we actually never released, hence I'm not naming them quite yet. But this is used in public transportation in France. That should limit it pretty well. A chip that's one of the oldest smart card chips that are kind of part of the current generation. It's kind of the first smart card chip in the current generation with meshes and all. May have been the first mesh ever. So this chip is crackable for, street price maybe 20,000. So who in the world is going to spend 20,000 to then ride the metro for free, right? That's more than a lifetime of metro rides. However, the exact same chip is stored in the reading terminals, deployed all over France and in remote locations. They get vandalized all the time, so these chips get lost with the master key for France in it. And again, 20,000 in attack cost for the capability of creating as many cards, kind of once-used cards, travel for free with as many people as you want forever until they replace the system. There may be a criminal business case, right? So it's not always the fault of the technology, but rather the people designing systems around it that makes technology insecure. And this exact same chip is secure on one side of the application and insecure on the other. The solution, I don't have to tell a technical audience like you is, of course, diversification of functionality, limit the abuse potential as much as possible, keep the value low for every single card, and keep it below, a couple of thousand, and nobody will do any type of actual key copying attacks. Do that in addition to publishing your software on the internet and forego any 10 years too late analysis where millions of cards have to be withdrawn, and smart cards can be an excellent security base. However, stop hiding any bugs in smart cards. With that, I'm pretty much through with the story, so thank you very much.
Yeah, thank you for this talk and for these insights. And are there any questions now?
No questions? No, thank you.
Oh, please go to the microphone there.
Oh, there are questions?
The first one to the IRC.
Do you the crypto in the card, since you have the data and the code, you can just simulate the crypto algorithm with the data and get the encrypted data without knowing anything about how works the crypto.
Which card are you asking about?
It is, do you need to reverse the crypto? I mean, since you can just simulate it, and you have all the data on the card just by...
The question is, do you have to reverse engineer the crypto since you can just simulate it instead? How do you simulate something that you don't know?
You have I mean, you don't have to know how to break the crypto. Just you have to look at the circuit and know.
Kind of like a cryptanalysis with an unknown function. Yes. That's interesting. We should explore the possibility if that had been possible now that we know what it is, but we didn't try that path. There's too many unknowns. Really, trying to analyze even a bad crypto function where you don't know the crypto function is incredibly hard. It would have to be like a simple XOR type function to have any success. We've tried that in the past and usually failed. So reverse engineering is kind of the guaranteed success route.
That was not the question, but...
Then let's talk later. I don't think I understand your question.
My question was, have the production, well, I guess, let me start over, I apologize. How much more does it cost, I just have no luck. How much more does it cost to put more things on the chip to increase the complexity of it? And have the manufacturing techniques for the chips been, focused on lowering the cost of increasing the complexity of the chips?
That's an excellent question. And the cost of a chip scales absolutely linearly with the size of the chip. So you have a certain cost per wafer, and the more chips you can put on the wafer, the cheaper every single chip. Meaning if you grow this by 10%, then the manufacturing cost is 10% larger. Adding, say, a new encryption function like AES, you see how little AES is. So adding AES probably made this chip 5% more expensive. And it's an excellent encryption function, much better than anything this card could have done before. So usually adding more smart security measures doesn't cost anything at all, really, in the big picture. However, of course, adding another layer of mesh, for instance, that grows the chip in the other dimension by 25 or 20%. So that's significant. So kind of the simple security measures with full coverage of the whole chip, they're usually expensive. The smart cryptographic solutions are not.
And then just one follow-up question to that, and forgive me if I'm not using the right term, but increasing the resolution of the chip, making the traces and making the chip points much smaller, is that currently happening, or are they focused on that at all or not? And would that increase the complexity?
They are surprisingly slow though. So the absolute new smart card chips that are just now coming out, they're manufactured in 90 nanometer feature size, where, of course, like NVIDIA, Intel, those companies, they are at 32 nanometers for the next generation. So there's like five generations ahead of smart card chips. But I guess that goes back to the volumes they are pushing. And compared to an Intel chip, smart cards are still low volume, since each customer needs slight adaptations to the chip. So every single run will always be small, and these new technologies, they're only accessible to somebody like Intel, who will produce the exact same chips dozens of millions of times.
So from newer chip designs that don't have ROM masks but store their application code in Flash, those chips would mitigate these attacks entirely.
They would, but there's really only one chip I can think of, and that's kind of, it's advertised as kind of like a rapid prototyping chip, not so much a production chip, because, like this chip has 224 kilobytes of ROM, I believe. That's the small area down here. And it has maybe 70K of flash. So if you were to convert all the ROM into flash, this chip is more than twice the size, or maybe 3 times the size. So usually people don't yet use flash-only chips. However, one exists at least.
But I don't think that's being implemented as a security purpose, but they can be used for different purposes then. I mean, it's just a stock management thing.
I like flash-only chips. If you can limit your application footprint to maybe the 72K that this chip already has, just don't use the ROM. Do in the ROM a jump to flash immediately, which allows you first to stay out of this type of analysis, which I don't think would be the security argument, but it will allow you to update your software in the field if you do find a bug, right? That's much more important.
How difficult do you think it would be to attack the flash by reading it directly without reading the bus going to the CPU.
Not possible, even with atomic force microscopes. Flash is so super optimized, the difference between a 0 and a 1 is virtually non-existent, so there's nothing you can measure.
No, not measuring it, but actually just, okay, you would have to, yeah, sorry.
Wait, there are two questions from the IRC. It's basically questions about the equipment you need to use. So the first one is, what equipment do you need to clean the layers and remove the mesh?
That's a good question for Starbuck. He optimized his techniques a lot. So I understand what he's using is polishing paste. So the finest polishing paste you can find on a rotating surface. And then he glues the chip to a block of plastic and kind of puts the chip on this rotating polishing paste for a couple seconds, maybe up to a minute, and then one layer is gone. Kristanovsky, on the other hand, he does this just with his finger. So he puts the chip on his finger, puts it on like a rotating disc with polishing paste. He kind of has a feel for when it's a little magic, but you know, practice makes perfect. Yeah.
And the second question is, what is the ideal equipment that we can use to contribute to this kind of work?
Well, I think at this point, where people would really make an impact is by starting using the DGAT software and doing all these reverse engineering steps between. Taking pictures is something that a lot of analysis labs offer for little money. So if you really want to do all the steps yourself, get a good optical microscope, but unless you do many reverse engineering problems, you may pay more for the microscope rather than having other people do the pictures for you. So at this point, it's not really an equipment question anymore. It's a question of people starting to find targets, having others take pictures for them, and reverse engineer them in this DGAT software.
Okay, thank you.
Thanks.
Since we are a little bit short of time, I would now to announce the last three questions there.
You said sometimes you can't update the software on the ROM, but in January 2010 all the EC cards in Europe or maybe just in Germany had problems and they were updated by just putting them into the ATM. How did this work?
Yeah, that surprised me, since the CC evaluation actually asked for certain things to not be temperable, and then they update it. So that's within my definition of temperable. I guess what they do is they, in ROM, have a hook that says something like, if certain things are written to flash at that and that position, execute those instead of the ROM. So they did like a patch management, a complicated way where the technology base doesn't usually allow for it. So there was definitely some good forward thinking there. But I'd be surprised to find that in a lot of smart card applications. I think most people just assume when a card is broken, send out a new card, just like PayTV does it.
I have no idea about hardware, but I've got a question about the layout. So here everything is in one block. Is there a hardware reason why they produce it like that? Because it could be completely random and every XOR function could be not just mirrored, it could also be random. Or is there a hardware reason why they do it like that simple?
No, it's more like a design process reason. So designing silicon gates and testing their functionality in all corner cases is hard work. So if you do this once for an XOR function and you prove that it works, then you don't want to do it again for the same chip. So there's a library of these very well-designed functions that people use. Just like you don't get to choose what assembly code you're using, the Intel gives you a list of codes to use. So that usually comes from the silicon manufacturer. That's not the chip design in a lot of cases, but today companies in Taiwan that just manufacture chips where they don't know what the chip does actually, and then the smart card manufacturers put a design to these companies to have it manufactured. So the smart card company then decides in how many blocks this is separate, that this, for instance, and this are two different blocks, and they of course do this to have separation of work. So one team can concentrate on a CPU core and one team can concentrate on the AES core, and they have these modular blocks, and then one customer may say, we don't want AES, so they take this out 5% cheaper, for instance. Right? So it's kind of, most software is modular. I don't see, any software that's just one large block of main and end, right? And hardware is same for reasons of refactoring and all.
But couldn't it be randomized after, like, when you compile it?
Well, the gate's not. That's just huge design overhead. And maybe you could get it to the point where there's 5 different options for XOR. But there's still 10,000 XORs on your chip, so they'll all be one of these 5. The other question, I guess, is can you merge the AES part and the CPU part and all of this? And this chip already does this. So everything that's random logic is in this one big block in the middle, and that's state of the art. However, one of the smart cards manufacturer has a patent on this, right? So the idea of kind of compiling all your object files into one big binary in hardware, that's patented.
Okay, some more questions from the IRC. First, the guy who spoke about the update of a flash card, can he come over? Because there is some guys in the IRC interested by that event. So if he can come over, well, if he's still in the room. There is a question about, is there people designing smart card that can be updated on the field? And
well, I think we've just answered that question around the German banking card. So maybe in violation of their own evaluation, the German banking card seems to be upgradable. But that's not the standard for smart cards. There's some trick they're playing, mixing kind of ROM and flash functionality.
And is there an additional cost linked to the construction of upgradable smart cards?
It's not an official field, and around the German ATM cards, it was not known that that's possible until they did it, and everybody was surprised. But they had an actual bug where cards stopped working. I guess what they did is they incremented in hex or something. So after after the year 10, the year 16 came, and they had to fix that, some little bug in some function, and they managed to change it on the fly by people using ATM machines. Yeah, but still, the protocols are definitely not documented publicly.
Okay, thank you very much.
They interpreted the year number as hexadecimal, so 2010 was not interpreted as 2010 but as 2016. So that was the problem.
How does the smart card industry in general react to the type of research you're doing? I mean, is there, what have your interactions with them been like?
Well, this industry is generally slow to react, since generating new design paradigms will take them anywhere between 5 and 10 years. So usually when you start designing a new card from scratch, you won't ship the first silicon until 5 years later. But so the people in the smart card industry who I am talking about this with, some of this they were of course aware of. Some other things they're now trying to add into the evaluation by changing point systems, or at least starting some discussion around whether they want to change point systems. But I don't think there's been any direct response to this research. I must say though that this, for instance, the card we analyzed is the second latest from this company, not the latest. So it'll be interesting to see whether in the absolute latest designs, the stuff that has come out this year or from other manufacturers will come out this year is any better. And again, this is kind of work that inside the company started 5 years ago. So I'm really curious to see whether 5 years ago they anticipated whether the cards that they designed 10 years ago had this kind of problem, and now they mitigated it. But in any practical sense, cards that come out this year won't be seen in wide adoption for many more years. So everything that is deployed, all these billions of cards, they have this problem, and it won't go away for another decade.
So I got some more minutes, so if there are some questions left, please ask them.
Have you faced any legal threats after your MyFair hack or
No.
these attacks? No. Okay.
So, are there any other questions? It does.
Yeah, oh yeah, DGAT is open source, good point.
Yeah.